We're going to continue with a review of arithmetic along with number theory, throwing in the number theory along with everything. Just to kind of see some of our patterns that develop in math. As I mentioned last week, we will end this unit next Monday. So on Wednesday, February 8th, will be our first unit test. I will get that sent out later this week so that you should have it at your location so it's ready to go. Just be prepared for that. So, as I said, we're going through these. I realize you have the calculator, but on the test, you will have to show some of your work and some of your steps in those calculations just to show that you're aware of the steps involved. So today, we're going to continue, as I said, we're going to expand one of our concepts, which is place value. And so we had looked at place values before, starting at the end of the number, the decimal point, and working our way backwards to the left. And we'd identified those place values as the ones, tens, hundreds, and of course repeating with different groups. But I want to look at it today in terms of powers, the basis of our number system. We have what's called a base 10 number system. The word decimal, by the way, means base 10. Deci is the prefix for 10. So we're dealing with a base 10 number system. Well, what does it mean to have a base of 10? Well, what it's actually talking about is powers or exponents. And we saw these a little bit before. Remember, if we have something like 8 to the power of 3, that is the exponent. And that exponent has two parts. The 8 is the base. That is the number that is being acted upon. And the 3 is the power. That is telling us how many times that 8 is repeated. So 8 being a base kind of leads us into the base 10 numbering system. The base 10 numbering system is exponents with a base of 10. So let's take a little bit of time to explore those powers of 10. So let's start out with just some random ones, like 10 to the third. We know that the third power means that we have 3 of those being multiplied together. So 10 to the third power is 10 times 10 times 10. You calculate that out, it comes to 1,000. Whereas 10 to the 7th power would be 7 tens multiplied together. Calculates out to be 10 million. On your calculator, by the way, you all have one of two keys. Either it looks like that, it's called the caret key. If you have some of the newer versions, that's what most of the newer calculators have. Or your cell phone or some of the older calculators have an X to the Y or Y to the X key, like something like that. And so to enter that in, my calculator has the caret key. So I would do 10 caret and then 7, and it gives me that 10 million. Well, most of you have probably been taught a pattern for the powers of 10 where just the power is the number of zeros on the result. 10 to the third, 3 zeros. 10 to the 7th, 7 zeros. And that's exactly true. That's one of the patterns that develops. So what I want to do is now I want to work backwards and figure out what are some of those powers, what are the meaning of some of those powers that don't necessarily make sense. So 10 to the power of 4 is 4 tens multiplied together. Using that pattern, of course, that would just be 10,000. 10 to the power of 3 zeros are 1,000. We just saw that up above. Well, let's keep going to establish a pattern. 10 to the power of 2 is 100. Now, if we look at what's going on here, each time we reduce the power by 1, our answer is divided by 10. 10,000 divided by 10 is 1,000. 1,000 divided by 10 is 100. We reduce the power by 1 again. So if I keep going and I reduce that power by 1 more, I get 10 to the power of 1. Well, we're dividing the answer by 10. 100 divided by 10 is just 10. Makes sense. Every number we have, even though there's no power written there, is to the power of 1. So 10 to the power of 1 is just itself. It's the next step that's interesting, that gets into that territory where the definition breaks down again. 10 to the power of 0. How can you have 0 tens multiplied together? Well, you really can't, but we can continue our pattern. The power was reduced by 1. We're going to divide this by 10 again. 10 divided by 10 would be 1. 10 to the power of 0 is 1. In fact, anything to the power of 0 is 1. In some of my college algebra courses, I used to ask questions like this. 19 to the power of 432 times 7 to the power of 189 divided by 3 to the power of 1,247 times 11 to the power of 86, all the power of 0. Well, what is that? Well, that's, of course, 1. Because no matter what all of this comes out to be, it's to the power of 0, and anything to the power of 0 is 1. Even x to the power of 0 is 1, which will be important when we get into our algebra section. So as we continue this then, 10 to the power of negative 1, well, obviously we can't have a negative number of items multiplied together, but we can still continue our pattern. 1 divided by 10 is 1/10. So 10 to the negative 2, 1/10 divided by 10 is 1/100th. And we can continue going. 10 to the negative 3, 1/100th divided by 10 is 1/1000th. And so we see the pattern develop here. 10 to the negative 3 is related to 10 to the third. They're just reciprocals. 10 to the power of negative 3 is 1 over 10 to the power of positive 3. So 10 to the power of negative 5 will be 1 over 10 to the power of positive 5, or 1/100,000. So now back to our place values. Now we can see that 1s is just 10 to the power of 0. 10s is just 10 to the power of 1. Hundreds is 10 to the power of 2. The 1,000s is 10 to the power of 3. The 10,000s, 10 to the 4. And just counting up those powers of 10. But now if we keep going to the right, the pattern has to continue. So each time we move over a spot, the power of 10 is reduced by 1. So this would be 10 to the negative 1, or 1/10. 10 to the negative 2, or 1/100th. 10 to the negative 3, or 1/1000th. 10 to the negative 4, or 1/10,000th, and continuing on down. Now, as we see these place values in the decimal places, you might start to think, well, geez, those place values look a lot like fractions. And they do, because that's what a decimal is. A decimal is nothing more than a shortcut way of expressing fractions that have those common denominators, or they're powers of 10. So if I have 0.874, that literally means the fraction, the 874, over the denominator of 1,000, 874,000. Now, as a fraction we saw on Friday, we can reduce that Both 874 and 1,000 are even, so we can divide them both by 2. That would be 437 over 500. And that cannot be reduced any further, so that would be the end of the line for us, 437 500ths. And it is that simple to convert a decimal back into a fraction. We might have 7.0625 as our decimal. So I'm going to take that 7.0625. First off, just like we have mixed numbers and fractions, we have mixed numbers in our decimals. The 7 here is just a whole number. It does not affect the decimal at all. So the 7 is going to stay. It's only the part after the decimal point that becomes the fraction. So now the part after the decimal point is just read as a number, 625. And the denominator is just the place value of that last digit. That 5 was in the 10,000ths place. Now, I'm not big on shortcuts, but here's a shortcut that's worth using. Way to double check to make sure you got the right denominator is there's 1, 2, 3, 4 decimal places. There better be 1, 2, 3, 4 zeros in that denominator. Every decimal place comes out to be a 0 in that denominator. Now, of course, that can be reduced. Both 625 and 10,000 can be reduced by 5, but you might see that both of them can be reduced by 25. There are actually bigger numbers they can be reduced by, but we'll start with the 25. So 625 divided by 25 is 25. 10,000 divided by 25 is 400. Now you can see that both of those can still be divided or reduced by 25. 25 divided by 25 is 1. 400 divided by 25 is 16. That is 1/16 is the fraction form. Now remember the whole number of 7, so that is 7 and 1/16. Now, just like any other number, when we add or subtract their decimals, we must have the same name. Now, with our fractions, that meant having a common denominator. Kind of does with our decimals as well, if you think of that fractional equivalent, but probably relates closer to our whole numbers where we had to line up the place values. With the decimals, we have to line up the place values to add or subtract. And usually the shortcut or the gimmick we use to make sure we line up the place values is to line up the decimal points. Again, the only purpose of lining up the decimals is to make sure we're lining up the place values so that we're combining things with the same name. And of course, we combine counts. Every operation, we combine counts. And then we keep the same name. And so for decimals, keeping the same name becomes just bringing the decimal straight down. So as we look at adding two decimal numbers, we might have 4.38 plus 23.794. So when I go to add these, I'll write my first number. Now, it doesn't matter which one you write first. I am usually used to writing the number with the most digits first, but you really don't have to. We could put the shorter number first. But because I have to line up the decimal point, typically before I put in the second number, I'll put the decimal point in first, and then I'll fill my digits around the decimal point. So the 23 goes in front, 0.794, and we are adding. Now before we start the addition, we should fill in any missing decimal places. If you recall from last Monday, That's making sure that both of these have the same name. These are now both thousandths. This is 380 thousandths on top and 794 thousandths on bottom. We're making sure they have the same name. Now we can go ahead and add. 0 plus 4 is 4. 8 plus 9 is 17. But just like whole numbers, we can't have two digits in the same place value. We keep the 7 and we carry the 1. 1 and 3 is 4, plus 7 is 11. Again, we have to carry, so we'll keep the 1 and carry the 1. Now you'll notice decimal point does not affect our carrying at all. We can carry right past it. But before we do this next digit, this next place value, we should bring down the decimal point. Now we have 1, 4, and 3, make 8, and 2. So 28.174. Not going to do any more examples of adding decimals because pretty simple. Line up the decimal point, add the numbers. And to be fair, pretty much even the cheapest calculators on the market do decimals pretty well. On the test, all I would require you to do is show lining it up and then give me the answer. I need to see that somewhere on there the decimal points are lined up. For subtraction, then, we follow the same process. We might have 42.63 minus 9.85. Now here, obviously, we have to put them in the right order because with subtraction, we can't change the orders. I put the 42.63 first. Now I'm going to put my decimal point in, so I make sure I line that up. Actually, I put 9.85. This should have been 9.854. Sorry about that. So I'll put my 9.854 in there. And we are subtracting now. Now, just like with addition, subtraction, I have to fill in that missing place. There's no option. Addition, I could have done it without filling it in, but subtraction, there's no way around it. So now we go to subtract. We have 0 minus 4 can't be done. To borrow. So the 3 becomes a 2. The 0 becomes a 10. 10 minus 4 is 6. Now 2 minus 5 can't be done. So we again have to borrow. 6 becomes a 5. 2 becomes a 12. 12 minus 5 is 7. 5 minus 8 cannot be done. So we have to borrow. 2 becomes a 1. The 5 becomes a 15. Again, notice the decimal point did not affect our borrowing at all. We borrowed right past it. 15 minus 8 is 7. However, now, again, before we move to that next place value, or next decimal place, we need to bring the decimal point straight down. 1 minus 9 can be done. We borrow from the 4. That's 3 and 11. 2 and 3. Again, I'm not going to waste time with a lot of basic subtraction. But there is one example that I do want to make sure we show. Something like this. 7 minus 4.8329. So when I go to subtract something like that, first of all, I need to know where the decimal point is in the 7. Because there isn't one written. If there's no decimal point written, of course, it's always at the end of the number. So that's 7 point whatever. So when I set this up, 7, my decimal point there. And then I have to line up around that decimal point. 4.839. And we're subtracting. Well, now here we have a bunch of zeros we have to fill in. We need to be careful. Make sure we line them up so we're filling in the right number of zeros, keeping them above the other digits. So now when we go to subtract, 0 minus 9 cannot be done, so we have to borrow. But there's nothing here to borrow from. So we have to keep going over until we hit something we can borrow from, which will be the 7. Again, notice the decimal point doesn't affect us. We borrow right past the decimal point. So we borrow from the 7, that's a 6. But when we borrow, it only goes to the next digit over. So this becomes a 10, and that's it. Well, we need to get it all the way down here. So we have to keep borrowing. Borrow from that 10, this becomes a 9, and now this is 10. We do it again. Borrow from that 10, this is a 9, and now this is a 10. And one more time. Borrow, this is 9, and now this is 10. Now we're down, we have values down here, so we can go ahead and subtract. 10 minus 9 is 1. 10 minus 2 is 7. 9 minus 3 is 6. 9 minus 8 is 1. Again, we have to bring the decimal point down before we cross it. 6 minus 4 is 2. So again, the point there was that sometimes we have to borrow more than once before we can even start to subtract. When we multiply or divide, we do not need the same name. Which means we don't, for decimals, means we don't have to worry about lining up the decimal point. We're going to combine the counts. Again, every operation we end up having to combine the counts in some form. But then we also combine the names. Now you might be getting sick of hearing these rules laid out over and over again, but we are going to see them. Other forms of numbers we're going to run into. They're going to keep following these same set of rules. So let's take a look at a basic decimal multiplication. 3.48 times 6.7. We didn't really do a lot of long multiplication with whole numbers, so this would be a good practice just to make sure we have one good solid long multiplication under our belt. So 3.48, 6.7. Notice I did not bother to line up the decimal points. We don't need to when we multiply. If you recall, we have to combine every digit of one number with every digit of the other number. We start with the last digit of the bottom number, which is the 7. And we combine it with the last digit of the top number, which is the 8. 7 times 8 is 56. We'll keep the 6 and carry the 5. Move to the next digit. 7 times 4 is 28, plus the 5 is 33. Keep the 3 and carry the 3. Notice we're completely ignoring the decimal places here because we don't have to keep the same name when we multiply. We're going to combine the names, so we can do that later. So 7 times 3 is 21, plus the other 3 is 24. So that's 4. We carry the 2. There's no more digits, so we just drop it down. Now, when we move over to the next digit, we put a 0 down here, as always. I'd also like to put a line up above to make sure I know that anything under the line is an old carry. I don't have to worry about it. I do see students make that mistake all the time. Nothing gets carried, but there's a number up there, so they add it anyway. They're not sure what was an old carry or a new carry. So that little line up there helps us prevent that confusion. So now we're moving over to the 6. Make a different color here. So we have 6 times the 8, which is 48. So that's 8, carry the 4. 6 times 4 is 24, plus 8 is 28. So that's 8, carry the 2. 6 times 3 is 18, plus the 2 is 20. So that's 0, carry the 2. Again, we're out of places, so we just drop the 2 down. And now we can add them up. 6 and 0 is 6. 3 and 8 is 11, so 1, carry the 1. 1 and 4 is 5, plus 8 is 13, so 3, carry the 1. 1, 2, and 0 is 3, and 2. So now it's that time to combine the names. And of course, the way we were taught to do that, you count 1, 2, 3 decimal places in the problem. Start at the end of your solution. You count backwards 1, 2, 3 decimal places in the answer. That's where your decimal point goes. Well, as we mentioned last week, all that is that this is hundredths. That's the last digit of that number. Last digit of this number is tenths. So when we combine those hundredths times tenths, the last digit of this number better be in the thousandths. And it is. When we're counting up those decimal places and making sure there's that many decimal places in the answer, all we are doing is combining the names. Well, let's get on to long division. Long division with our decimals, because of the shortcuts we were taught with whole numbers, almost becomes more complicated. If I have something like, let's make sure I got one that comes out here. So let's do 149.155. Actually, let's do this. 149.1596 divided by 2.3. We're going to come back and do this the traditional way in just a second. But remember what we saw on Wednesday last week with the long division, where we're doing the place values and multiplying for repeated subtraction. Here's the same way. Now, we do have to correct our place values a little bit sometimes because we're dividing by a decimal. So we might actually have a place value bigger than what the place value is and what we're dividing into. But here we could try on hundreds. Hundreds is that place value. 100 times 2.3 is 230. We can't subtract that. It's too big. So we go to the next place value. Tens times 2.3 is 23. We could subtract that. That would be 6 times, I believe. So would that be 138? We subtract that, we got 11.1596. So again, that's 10 times 6, or 60 times that we've subtracted the 2.3. And we can keep going in that process, going to the ones and then the tenths and the hundredths, and it would work out just fine. We would just add up our results up top here. But remember, we've shortcutted that process so that we didn't have to write this out and this part out here. What we have done is tried to do just working with a couple digits at a time. So the way we've done it is we've taken out dividing by the decimal. We changed a problem like this into, instead of dividing by 2.3, dividing by 23. And then, of course, by changing that to 23, this has to be changed to 1,481.596. Why were we able to do that? Well, because we've mentioned a couple of times that there's a link between fractions and division. We can switch very quickly, very conveniently between a fraction and division, or division and a fraction. So we can think of this as a fraction, 149.1596 over 2.3. And in a fraction, we can multiply numerator and denominator by the same thing. And since there's only one decimal place here, to get rid of the decimal, I just multiply by 10. Multiplying by 10 on top gives me 1,481.596. Multiplying by 10 on bottom gives me 23. Now, if there were 2 decimal places here, we would have multiplied by 100. 3 decimal places by 1,000, and so on. So when we've been told that we have to move this decimal point over to the end of the number, then however many places that moves, we have to move this one the same number of places. The reason is because we're creating equivalent fractions. We're using the fraction form of the division problem to create equivalent fractions and then turning it back into a division problem. So anyway, now we have to do the division with the decimal still in our divisor, or the dividend, I should say. Let's say that we want this to the nearest 10,000th. So let's see how that goes. Nearest 10,000th, we want our answer. Well, we start off, 23 does not go into 1, so we leave it blank above the 1. 23 does not go into 14, so we leave it blank above the 14. 23 does go into 49 6 times. Notice that's basically what we saw up above. The 60, well, the 6 is in the tens place, so it is a 60. We go ahead and subtract, we have 11 left over. Now we bring down the next digit, which is the 1. 23 goes into 111 4 times. 4 times 23 is 96. We subtract there, we have 18 left. Now, before I can bring down the 5, I cross the decimal points. I have to bring the decimal point straight up. Now, you might say, well, why do we bring it straight up? I thought we had to combine names when we divided. Well, in the division process, things kind of go backwards. We actually combined the names before we started. Moving the decimal points over here, using that fraction equivalency, that is already combined the names. So the names are already combined. We just have to move the decimal straight up at this point. 23 into 155 is 6 again, I believe. That's 138. We have 17. Bring down the 9. 179 going in, or 23 going into 179. 8 will not quite go. We have to go 7. 23 times 7, 7 times 3 is 21. 2, 7 times 2 is 14, plus 2 is 6. So 161. We have 18 left over. We bring down the 6. 23 goes into 186. Oh, let's go. 9 ain't going to do it. Let's go 8 times. 8 times 23. 8 times 3 is 24. Carry the 2. 8 times 2 is 16, plus 2 is 18. We have 2 left over. So now we're out of digits up here. But now since we're after the decimal point, we can add more zeros if we want to. I can put another 0 here and bring it down. This is now 20. However, 23 does not go into 20. I put a 0 up here. Now we said we wanted this to the nearest 10,000ths. This is the 10,000th place. Are we done? Not quite. Because we want to the nearest 10,000ths implies we have to round to the 10,000ths. And in order to round, remember, we need to know what the next digit is. So we have to go one more digit, so add one more 0 and bring it down. 23 goes into 200 8 times. 8 times 3, we just had it up here. It's 4, carry the 2. 8 times 2 is 16, that's 184. There's 16 left over. So now when we look at this, we're rounding to the nearest 10,000th, so the 0 is in the 10,000ths place. That next digit is an 8. So to the nearest 10,000th, this is 64.6781. Now, long division, I realize is the one operation I try not to do by hand because it sucks. But again, on the test, I would at least expect you to convert from this to this, showing that the decimal point's been moved over. There are some relationships here between our decimals and really large numbers that I want to point out. For example, if I have 200 times 40,000. If we wrote this out with count in the name, this is 2 hundreds. This is 4 10,000s. Well, I'd multiply out, combining counts, 2 times 4 is 8. Hundreds times 10,000s is millions. That's 8 followed by 6 zeros. 8 is in the millions place. But the shortcut we have all learned for this is you multiply the leading digits. 2 times 4 gives us the 8. And then you combine the zeros. You have 1, 2, 3, 4, 5, 6. This is 2 zeros here, 4 zeros here. 2 plus 4 is 6. You have 6 zeros in your answer. I might have 30,000 times 200,000. I'm just going to do 3 times 2 is 6. I have 4 zeros here, 5 zeros here. So I'm going to have 9 zeros in my answer. 1, 2, 3, 4, 5, 6, 7, 8, 9. That is 6 billion. Why is that significant? Well, because a very similar, very closely related pattern occurs in our decimals. I have 0.04 times 0.0002. This has 2 decimal places. This has 4 decimal places. I combine my leading digits. 4 times 2 is 8. And I'm going to add my decimal places. I'm going to have 1, 2, 3, 4, 5, 6 decimal places. Now it's not 6 zeros that are being combined. Now it's 6 decimal places. The reason for that is, of course, this is 4 hundredths. This is 2 10,000ths. Hundredths times 10,000ths is millions. And so we have to get to that 6th decimal place to get to our millions. Division then has a similar related pattern. If I have 8 million divided by 200, well, again, we combine the leading digits. 8 divided by 2 is 4. But then now when we look at zeros, this one has 6 zeros. This only has 2 zeros. Now we're dividing. Just like our powers on our exponents, we subtracted the powers when we divided with the same base. We do the same here. 6 minus 2 is 4. We have to have 4 zeros on that result. So 40,000 is that result. Our similar pattern for decimals would be 0.00006 divided by 0.03. Well, again, we have the trailing digit now, not a leading digit, but we divide 6 divided by 3, of course, is 2. And the number of decimal places now is what we count instead of the number of zeros. Here we have 5 decimal places. Here we have 2. 5 minus 2 gives us 3. We're going to need 3 decimal places here. We have 1, 2, 3. 0.002 is that result. Now again, it comes from combining the names. This is 600,000ths. This is 300ths. 100,000ths divided by hundredths is simply thousandths. Now again, I know that you all knew this. That's why I didn't do a lot of examples of it. But I want you to start to see those links and connections, the similarities from one form of a number to another. The similarities between working with whole numbers with a lot of zeros, working with decimals, working with powers of 10 or other powers and exponents. They're all the same rules, they just look slightly different because they're different forms of the number. Now as we look at our last set of operations, powers and roots, we want to look at taking like 0.4 squared. Well, 0.4 squared, of course, means 0.4 times 0.4. Multiply that out. 4 times 4 is 16. 1, 2 decimal places. You get 2 decimal places. 0.16. That one's relatively predictable. The one thing we do have to remember is when we multiply by something smaller than 1, we get a result smaller than 1. So something like 0.02 to the power of 3 is going to get small very, very fast. That's 0.02 times 0.02 times 0.02. Now I'm going to take a little bit of a shortcut to speed this up. 2 times 2 times 2 is 8. but I have 2, 4, 6 decimal places total. My answer has to have 6 decimal places. So that's 1, 2, 3, 4, 5, 6. So 0.000008 is that result. This was the original number had 2 decimal places to the power of 3. 2 times 3 is 6. Our answer had 6 decimal places. This is related to that again, that power, the rule of exponents, where if I have x to the third to the power of 4, I multiply the exponents. That's x to the 12th. Well, the same here is the decimal places. 2 decimal places to the power of 3 gives me 6 decimal places in my answer. What that means is going the other direction during a root. If I have something like the square root of 2.5, at first glance it looks like, well, that's easy enough. We can do that. But the problem is when the square root is asking us to do the reverse of squaring something. If we square a decimal with 1 decimal, any decimal with 1 decimal place, we're going to get 2 decimal places. If we have, 5.1 squared, here we go. We end up getting 26.01. We get 2 decimal places. Or if I have 7.8 squared, 60.84, again, 2 decimal places. There is no number that we can square that'll give us just 1 decimal place. So if we go to square root 2.5, and I know you guys know how to use the calculator function for square root, we are going to get an ugly decimal. It doesn't come out to a nice, neat little decimal. We look at the 2.5 and we're thinking 25, which of course is a square root of 5. We think, well, that should work out, but it doesn't. And one of the things with roots is any root that does not come out to a nice even number, I shouldn't say even, but a nice neat number has this effect. It ends up being what we call irrational. It's non-terminating, non-repeating decimal. So that decimal actually goes on forever, even though only the 8 or 10 digits display on our calculator screen. Okay, with that, we've hit our time, so I'm going to give you guys your homework. Page 29 through 32. Now, it's 1 through 91, the odds. As always, if those first few seem easy, skip over them. Make sure you do the word problems because there will be a lot of word problems on the test. Pay special attention to rounding with decimals. For some reason, the rounding problems are ones that people always tend to get wrong at a higher rate on this first exam coming. So with that, does anybody have any questions? Okay, well, you guys have a great day. We'll see you all on Wednesday.